Ladies and gentlemen, welcome to this sixth lecture on the short course for seismic isolation. So this is the last week, the second and last week of the short course. And as I mentioned last week, I will do with you some actually practical applications on what we have seen together about generally the pre-design of isolation systems, and then we will carry out some numerical assessments. And we will be able to perform some nonlinear time history analysis with both a commercial software, which will be SAP 2000, and we will use it deeply into the details on Wednesday afternoon, where there will be the second numerical laboratory of the short course. And again, I just want to highlight that if you don't have the commercial software installed in your laptop, so you need actually software to use it, just email to me, and I will provide the access to a remote desktop, which is actually here in my faculty, and in that computer there will be the commercial software installed, so that you will be able also to follow all the computations that we will do. So before the numerical laboratory on Wednesday, we have just to cover some topics. First of all, we have to define actually the case study structure that we will use for these practical applications, so for this laboratory. And this is what we are going to do today. And tomorrow we will do another very important issue, which is actually the selection of seismic events for nonlinear time history analysis. And we will see some, some strategies to do it according to, we will consider the Italian building code, but actually the procedure that we show you can be applied to whatever standard code worldwide. So whatever is the target spectrum for spectrum compatibility, each code, every country has actually its own rules for spectrum compatibility. Generally, it is defined according to this acceleration spectrum. And we will see what is actually ruled by the Italian building code within the Italian territory. And we will try to use a database which generally is not known to be available to practitioners, and we will use actually the database of Rex software by Iervolino et al., which is already useful to provide selections for natural seismic events by itself, which is just a graphical interface software implemented into the MATLAB environment, but it is actually an executable file which is separated, but with respect to MATLAB, you have just to install some additional toolbox, but something very, very easy and very fast. But then what I generally do in my research activity is, okay, maybe sometimes I use just the software itself as it is, or maybe for some specific application where I want to better control the selection of the seismic events, I just use the database which is implemented and stored within the program. And then I just use it within a MATLAB environment. I just write a script and a specific script for the selection with the selection rules that I define. And I don't use a black box software, but I want to actually provide my selection rules. So this is actually what we are going to do tomorrow. And once we have the case study structure today, and tomorrow we will have also the selection of seismic input, we will be able to perform the numerical laboratory with the nonlinear time history analysis. So we will be able to implement and to model with the finite element models within SAP 2000 the case study structure, and then to carry out actually nonlinear time history analysis. So before starting, as generally we do at the beginning of the lectures, I ask if there is any question about what we have seen last week for all the lectures. Today, actually, we will cover again the fast design rules, but not from the theory point of view, but we will actually practice with some numbers and we will specify all the rules to the case study structure that we are going to define. So is there any question? Okay, if not, feel free to ask whenever, also during lecture. So I start sharing my screen, and actually for all the equations that we will have to use for fast design, I will not refer to the slides of last week, but I just directly go to the research article I provided also in our shared folder, which is actually the research article I've authored about the fast design procedures. And in that document, there is actually the whole procedure for all the typologies of devices, which is fully listed and with also additional details. So you can go back to the slides, but also you can go into that document, which is actually the more comprehensive document with all these rules. So I just share my screen. And let's start with just 2 slides with the main characteristics of the case study structure. You will see it is a very simple one, but we will just carry out some end computations at the beginning just to come up with one of the key parameters that we have to define for pre-design, which is actually the total mass of the overall system. And then afterwards, we will go through all the procedures for fast design. So these are the main characteristics for our structure. A very easy structure, which consists of a 3D reinforced concrete frame building. And we will consider 5 spans along the X direction and 3 spans along the Y direction, and 3 story, okay? So this is a very small structure, but it is useful for us to practice with the fast design, and then with the numerical assessment through the nonlinear time history analysis. And what I want to face actually with you is the same procedure, but with all the typologies of isolation devices that we have considered last week. So we will do exactly the same with rubber bearings, lead rubber bearings, and curved surface sliders. So we will face all the issues for modeling in SAP 2000 of such devices. So we will have hybrid systems, most probably for rubber bearings and lead rubber bearings. So we will have also to model flat sliders, and then we will consider also curved surface slider isolators through the nonlinear links that we have mentioned last week. So the special links, which provides actually the proper modeling assumption, so the theoretical response for such devices. And the special link is actually because the lateral force of the device is directly a function of the applied vertical load to the device itself. And the most important issue is that the applied vertical, and it is like that, the applied vertical load varies stepwise during the whole duration of motion. Such a variation will be also applied with respect to the horizontal loading. So we will also notice the variation of the force response also along the horizontal directions as a function of the vertical one. This is very important. This is not what happens if we want to model curved surface sliders through elastoplastic behavior, because elastoplastic links within SAP 2000, but generally also in OpenSys, just provide a specific horizontal hysteretic loop, but without the interaction between the vertical and the lateral force response. You need a specific, actually a specific link, which are also implemented in OpenSys, but specifically we will see what happens and what we have to define within SAP 2000. And whenever we have to carry out a sort of practical application, we do have to define the design actually of the case study structure, but we also have to define the prescriptions about the seismic input. So according at the beginning of our definition of the case study structure, the seismic input will be will be considered as the target spectrum provided by the Italian building code according to the following assumptions. So the collapse limit state, which is related to 5% of probability of exceedance within the reference life, which is assumed for 50 years for building generally, for ordinary buildings, let's say. And the collapse limit state for Italian building code is mandatory whenever we have to check the properties and the properly work of the isolation devices. So whenever we have to consider isolators to check the displacement demand and so on, we have to consider the collapse limit state. Whereas whenever we have to switch to the analysis of the superstructure, we have to consider the another ultimate limit state, which is actually 10% of probability of exceedance within the reference life. So we will consider the worst case ever of the provided by the Italian building code, which is actually 5% of probability of exceedance. And this probability ratio within this reference life provides a return period for the seismic input equal to 975 years. Then we will consider also the soil classification C, which is an intermediate classification of soil. So it is not a stiff soil, but it is not also too much flexible. And then topographic category T1. And we will consider the seismic hazard located related to L'Aquila city in Italy, which is one of the locations in Italy where we have the highest seismic hazard in terms of actually peak ground acceleration values. And this is actually the key parameter according to which the seismic hazard is defined along the overall territory of Italy. Then we know, obviously, we need also not only the peak ground acceleration, but we need also an estimation of the corner period and also the, let's say, the ratio between the plateau spectral coordinate and the initial value at zero value of period. So these are the three main parameters that we need for the proper definition of the seismic hazard in terms of the response spectrum of acceleration values. So let's perform some hand computations just to come up with the key value that we will have to use, the key characteristics of the case study structure that we will use for fast design. And then obviously on Wednesday, we will build up our building by considering actually all the quantities that we are going to consider now. So we know that the main characteristics for the building is just to consider a 3-story building with 5 spans along X and 3 spans along Y. So I just start by considering some of these characteristics. So 5 spans along X. This means 4 beams. 5 beams and 6 columns. Okay. and we have 3 spans along Y, and this means 3 beams and 4 columns. Okay, and we have 3 stories. Okay, for let's say the analysis of all the external loads which are applied, let's consider a flooring system with the following external loads. So the flooring system loads. So we will consider permanent structural loads, characteristic value, so G1K equal to 3.0 kilonewton over square meters. So these are permanent structural loads. Then we will consider G2K, which are permanent non-structural loads, equal to 2.0 kilonewton over square meters, which are permanent non-structural loads. And let's consider some live loads. So depending on the, the typology of the building, let's consider just ordinary buildings for houses, for residential buildings, let's say. So we will consider live loads, Q characteristic value directly equal to 2.0 kilonewton over square meters, as ruled by the Italian building code. So these are live loads for residential buildings. Okay, so these are the main external loads that we have to consider, and together with all these informations, obviously we don't know the sizes, even though we will guess some of them, and we will try to very fastly pre-design some external loads very easily. But according to these informations of external loads and the geometry that we know about the overall behavior, the overall developing of the geometrical developing of the building, we will come up with an estimation, a rough estimation of the global mass of the overall system. So we have to actually to define the span length for both the directions. For sake of simplicity, we will consider just equal spans for different spans for X and Y, but equal spans for all the beams along the same direction. So let's consider Lx, so the span length along the X direction equal to 5 meters. Whereas we will consider Ly, so the span length along the Y, equal to 4 meters. And we will consider the interstory height equal to 3.2 meters. Okay. So generally, we have these characteristics. This is a very easy case study structure. We will consider these plan view of the building. So we have 6 columns along the X direction. And then we have 3 spans and 4 columns along the Y. So again, so we have these grid for the plan view of the overall building. So this allows us to consider the maximum sizes of the building, the planned dimensions, I mean. Okay. So all these are columns for the building. Okay, so we have 5 spans along X and 3 spans along Y. Perfect. And generally, this is very helpful for us because according to this plan view, we can automatically notice a very important parameter for the design of the isolation system. As you may remind, last week we have defined all the parameters that we have to initially know. And the first information that we get from this drawing is that we have actually 6x4 columns, and generally isolation nowadays actually the common practice, according to the common practice, we generally install isolation devices just below the columns, and so this means that we will have 6x4 isolation devices, or generally structural bearing points. Okay, so the total number of structural bearings should be 24. Okay, this is a very important information, because then we will, whenever we will do, we will actually deal with the rubber bearings rather than lead rubber bearings. We will get a final number of isolation devices, and generally we will have to check if this number will be lower than or equal to 24, which is actually the number of structural bearings. If it is not, as it will be most probable, we will have to consider a hybrid system, so rubber bearings or lead rubber bearings together with flat sliders. So according to this definition of the geometry of our case study structure, we have the number of structural bearing points. Okay, which is 24. Okay, and generally we install isolation devices just beneath the columns, simply because in this way you are not actually providing and causing additional flexural internal forces within the interface between actually the isolation system and the superstructure, just because the columns are aligned with respect to the isolation devices. And also, according to this definition, there will be a more direct application of the vertical load to the devices, simply because the columns are vertically aligned with respect to the isolators. So, there are a number of applications where this doesn't happen. First, one of the most famous within the Italian territory is Progetto Casa at L'Aquila. There are some cases for that project where we have actually isolators which are not perfectly aligned with respect to the columns. Okay, there is no problem, because if you properly design the reinforced concrete slab, which represents the interface between the superstructure and the isolators, according to the flexural additional forces, internal forces induced by those locations and those actually structural layouts. But generally nowadays, what happens is that you find and you design isolators just at the same location of columns of the superstructure. And according to these, we can also define, as I mentioned before, the maximum sizes, horizontal sizes of the building. So this means that we have the span length, which is along Y 4 meters. So we have 4x3 because we have 3 spans. So we have 12 meters along the Y direction, whereas we have 5 spans of 5 meters length, and so we have 5 by 5, 25 meters. Okay, so approximately the length, the size along the x direction is approximately doubled with respect to the length, the size along the y. Okay, and this is helpful because we still have to design, and I mean not design, but generally to define the interface between the superstructure and the isolation system. And we can do whatever. That could be just a general flooring system, but what is commonly done in the common practice is to consider a reinforced concrete slab. For instance, in Progetto Case, there is a reinforced concrete slab for generally 3-story buildings, and the depth, the thickness of that slab is half a meter, and generally it is exactly like this building that we are designing now. And so we can just consider the plan sizes of that plate as exactly the sizes of the building, but we have also to consider just 1.5 meters for both the for all the edges as an additional length in order to provide the proper space where people can go through, and so on. So we will have to consider the reinforced concrete plate, which is actually the interface between the superstructure and the isolation system of Lx. So the total size equal to 25 plus twice 1.5, which is equal to 28 meters, and Ly equal to, again, 12 plus twice 1.5 equal to, so this is equal, okay, so we have 15 meters. Okay, so that we have actually something like this. The developing of this slab will be just slightly higher, I mean slightly larger with respect to the geometrical developing of the building. Okay, something like this. Okay.
Can I ask something, please?
Yes.
So if you want to install an isolation system, I think there is no possibility to consider the RC plates like, separated footings like you do in non-isolated buildings. It should be always like a full plate that covers the whole building, right?
Well, there could be also this beams among all the isolators. That could be also another application type, but the most common solution which is adopted in the common practice is to consider just a plate. But surely you can have just maybe just a general flooring system and beams. In this way, I think the reinforced concrete plate has the best behavior generally for the proper distribution of shear forces among all the devices which are implemented.
Yes.
Obviously, as you may know, it is from the costs point of view, it costs a lot more with respect to beams, just beams, but generally this provides a better behavior.
Yeah, okay, thank you.
Yeah, you're welcome. So this is the thickness of the additional geometrical plan development for the RC plate. So this is 1.5 meters. So this is why we get those sizes. And let's consider the thickness. So let's TP, the thickness of the plate, equal to 0.5 meters, so half a meter. So generally, you have to pre-design that according to some external loads definition. But okay, in this case, we can just guess it as a common parameter, which is assumed in design for also similar buildings which have been already realized. So according to this, we can, I think, we can go through some computations. I just want you to consider some very fast rules to get the global mass, because now we have to consider this developing of our building. We will have actually 4 isolators along the y direction. Then we have defined the plate, and then we will have the building with 3 stories. Okay, so 1, 2, and 3. So this is the lateral view of our building. We have 3.2 meters for interstory height. So let's consider this distance as the distance between the centroidal lines of all the floors, and this is 3.2 meters. Okay. And according to this, we have to consider also all the external loads which are applied and smeared, equally smeared to all the floors, and the same here, and so on. So the external loads will be considered and computed according to the numerical values I provided at the beginning. So let's consider now some fast rule. What we don't know is actually the permanent load, so the self-weight of the structural components that we are implementing, because what we have defined at the beginning as G1K, so the permanent structural loads are just referred to the flooring system. So this means that at this stage, we don't know the weight of the, of beams and columns, and we can compute actually the weight for the plate, but we still have to design some sizes, some geometrical properties for all the beams and columns. So generally, for a 3-story building, we can assume that we have, I think, columns 300 by 300 millimeters. Okay, and beams. Let's assume that for beams, we consider the h over the actually the width of the beams, which is lower than 1. Okay, so the height of the building is lower than the width, and we can consider 400 millimeters times the thickness of the flooring system, which could be 250 millimeters. Okay, and according to these sizes, we can just come up with the masses and the external loads for that. We will also have to consider another issue, which will be actually an issue for modeling, which is the general definition of the flooring system. So we have these okay, these are the y, and this is along the x. Okay, we have to define for the flooring system the direction of the main resistance against the external loads, the gravity loads. So let's consider this is the X and Y reference system. So let's consider that we have actually this definition of the flooring system, and this means that this is a single resistance flooring system, and so this means that the largest amount of external loads are applied to the X spans, whereas there is a very limited value of external load which is applied to the Y direction for all the beams, because we will assume the same principle for all the regions of our floor. Okay. Okay, so this means that if I just look at this region, we will consider the following definition of external loads. So we will have 40% of the total of the resultant load for this portion of the floor to the X spans, whereas we will have just 10% for all the Y spans. Okay, and then we will have, obviously, whenever we have an internal beam, we have to sum all the contributions, because we will have 10% coming from here, but we will have also 10% coming from here. Okay, and but this will be actually what we will consider on Wednesday, just to apply external loads to the overall structure. Okay, I think that together with all these characteristics, we can come up with the total mass, and we can start actually by computing and by defining the overall isolation systems. So I guess we are ready to switch to the Excel. Okay, and then we will actually try to design our systems. Okay, so let's compute the total mass of the case study structure. So computation of total mass. So the main information that we need are generally sizes, and for beams, columns, the plate. Okay, so let's start from the plate because it is directly defined. So RC plate, which is again the interface between the isolation system and the superstructure. We have Lx, Ly, and Tp. All of them are in meters. So Lx was equal to 25 plus 2 times 1.5, which was 28, and the same for Ly, 12 plus twice 1.5, 15, and the thickness was 0.5. So let's compute the mass for this reinforced concrete plate. We know the mass per unit volume, which is actually mass over, let's say, per unit volume. So this is tons over meter cubed, and a general value can be 2.5. Okay. So according to this, we know the mass of the overall plate. So the MP, let's call it MP, tons, equal to the multiplication of all these four numbers. So the mass per unit volume times all the sizes in the 3 dimensions. So times Lx times Ly and times the thickness. Okay, so we have a huge plate because it is very large in sizes, in the horizontal sizes point of view, and we have 500 tons approximately, slightly larger value. Okay, so this will be the first contribution for our total mass of the overall case study structure. So now let's try to compute the mass of the frame. Okay, let's say frame structure. And actually, we can compute the mass of a single story, and then we can multiply it by the number of stories. So let's define the one cell, which is the number of stories, which is just a number, and we have 3 stories. Okay. We try to do this in this way so that at the end you have just a very easy spreadsheet in Excel. So you can just change some numbers and you get with you come up with another definition of a case study structure, and you can practice. So let's consider now all the beams and all the columns. So we have the interstory height in meters, which is 3.2 meters. Okay. Then we have the span length along the x direction, which is 5, and the same along the y, which is 4. Okay. Then we have sizes of the sections for the x direction. Okay, I mean, generally we have beams with equal section. So let's consider B and H for the beam. So we have 0.4 and 0.25. Okay, this is for beams. Let's call it BB and HB, so beams. And then we have actually the same for the columns, BC and HC, but they are equal to the same number, equal to 0.3 meters. Okay. So the again, we need, this is a reinforced concrete frame. So we need again the mass per unit volume. We just recall the number and we set it equal to this, simply because it is a reinforced concrete. We want to account for the same numerical definition of mass per unit volume. And then let's consider the mass of a single story, which is actually tons. And we have to actually consider all the beams that we have along the x and y directions. We don't have actually the number of beams. Okay, we can just set it here and Lx just as a number, and the same here, and Ly as a number. We have 5 spans along the x and 3 spans along the y. So we have, so the mass of the single story is represented by all these spans that we, I mean, all the beams that we have in a single story, but we have also to consider all the columns. Okay, so let's consider this 2.5, because we have a reinforced concrete for both beams and the columns, which multiplies a lot of things. So let's start from beams. The beams are the following. I think that we can do like this. Number of stories, a number of spans along the X times the span length along the X times the sizes of the section. Okay. So now we have the spans. Okay. And we have to multiply these times the number of the spans along the Y plus 1. Okay, because in this way we have mass per unit volume. Okay, it is just before all the computations, because we have reinforced concrete for all the elements. Then times number of span lengths, number of spans along the X for a single, actually for a single beam, times the span length times the sizes of the section times the number of beams along the X. So this means that we have it is the number of spans along the Y plus 1. And then similarly, we have to do the same for the Y direction. So plus we have the number of the spans along the Y times the span length along the Y times okay, sizes for beams which are the same. Okay, times number of beams generally along Y, which is number of X spans plus 1. Okay, and this is just related to beams. Then we have to sum up all the columns, and columns are just the interstory height times the sizes of the section of the columns times the number of columns, and number of columns are actually number of span lengths along the X plus 1 times number of span lengths along Y plus 1, and then that's it. And I think we are done. So you see it is not a huge value, simply because this is just the structural components mass. So it is directly related to the frame itself. Okay, do you have any question about this? It is quite straightforward, just the summation of all the element masses. So this is just a single story, and then the total mass of the frame is equal to the single story frame mass times the number of stories. So 180 tons, 81. Okay, so this is the mass for just the frame. And then we have to consider also the external loads, because maybe I didn't mention it before. We have to remind that the mass, and this will be very important when we will have to define the nonlinear time history analysis within SAP 2000, we will have to consider the structural mass for our structure, for our building, which is returned by this combination according to the Italian building code, G1K plus G2K plus 30% of live load. Okay, so this is generally a seismic combination. This can be associated both to external loads and masses. Okay, so we have to consider exactly the same combination for external loads and mass. We have to keep in mind this G1K is represented by both the frame and the plate masses together with also the structural mass coming from the G1K of the flooring system. G2K is directly related to the non-structural permanent external loads related to the flooring system, and the QK is just the live load defined according to the residential building typology. Okay, so now we have to compute the mass related to the flooring system. Okay. Okay, so according to the flooring system, we have some information. We have, let's again write here the numerical values of the external loads. So G1K, so the permanent structural loads for the flooring system, which are kilonewton along on a meter squared. And these were 3. Then we have non-structural permanent loads, which were 2. Okay, and then we have live load, the characteristic value, same units, kilonewton per square meters, and we have again 2. And this is for, again, residential buildings. Okay, so we have the information of, let's say, Lx of the floor, Ly, and these are the Lx was 25 meters and the Ly was 12. So the M floor of the in terms of tons is equal to the area of the floor times the combination of the external loads that I've shown before. So this means G1K plus G2K plus 30% of live loads. Okay, but I've not finished simply because what we want to compute now is a mass, so in tons, and these are external loads which are in kilonewtons. So I have to divide the result by the acceleration, the gravity acceleration, so 9.81 meter per square second. Okay, and this is the mass related to the flooring system of a single floor, of a single story. We need to compute the total. Okay, we have the number of stories, which is a number, which is 3. And we have the total mass of the flooring system in tons, which is 3 times the mass of the single floor. And this is it. Okay. So according to this, we can actually consider also another important important contribution, which is maybe missing here. Because if we go back to the definition, okay, this one, okay, if we look at this scheme, okay, we have external loads for all the stories, but we have also external loads also for the ground floor. Okay, we don't have the G1K, but we will have G2K and QK, 30% of it. Because here G1K is already represented by the mass of the plate. Okay, so we still have to account for an additional contribution at the ground floor. So we have to sum up this contribution in this amount. So the total mass of the flooring systems. Okay, this is like this, but then I have to add actually the following, which is again the area of the floor times we just need G2K plus 0.3 times Q. okay, divided by 9.81. Okay, you see that it is a very small amount, but we still need to consider it. Okay. Any questions so far? Okay. So now we have all the contributions, which is actually the reinforced concrete plate, which is 500 tons. Then we have approximately 200 tons of the frame, and then we have okay, 600 for the flooring systems. So the total mass of the case study structure what we call the M total in tons is equal to the summation of all the contributions. So the mass or the total mass of the flooring systems, so coming from the external loads, plus the mass of the actually of the frame, plus the mass of the plate. So we have 1,300, approximately 300 tons. So this is the mass for the overall case study structure. Okay, and we need to consider this value for the pre-design of the isolation systems. So we will start from this value, and according to all the typologies, I mean, of the isolation devices that we want to account for, we will come up to the mechanical properties and the geometrical characteristics for all the isolators. Okay. So if there is no question about this very fast computation, so you see that these are just hand computations for the computation of the total mass, which is actually this one. Now, okay, let's go total mass. We can start from this value for the definition of all the isolation system. Let's start from rubber bearings, RB. So let's start from design of RB isolation system. Okay. So there is some missing because we know that we need the global mass of the structural system that we want to consider, but obviously we need also the seismic input for design. Okay, so for the definition of the seismic input, okay, for this particular application, we have to consider, as I've shown in the second slide of today, the collapse limit state for the Italian building code, soil classification C, topographic category T1, and the L'Aquila city in Italy for the construction site for the case study structure. So let's consider all these parameters. And generally in Italy, we have a tool which is very useful, which is actually an Excel spreadsheet which provides, okay, I'm sorry that it is in Italian, but unfortunately there was no English translation. You have different phases. We have to consider the actual region for the city. L'Aquila is the province, and then the city itself. Okay. And then there is the interpolation, surface interpolation, actually, for all the among all the cities where the parameters for the seismic hazard are already defined. We have the nominal life 50 years together with a classification factor equal to 1 because it is not a strategic building. And then we will consider 5 probability of exceedance within the nominal reference life, which is again 975 years as a return period value. And then we have the third phase, which returns the response spectrum. Okay, we have to just select SLC, which is related to the collapse limit state, the soil characteristic C, and topographic category T1. What I didn't mention before is that for design, we need the elastic spectrum and with directly associated to 5% damping. This is very important because we will account for the proper damping of the isolation system directly within our computations in Excel. Okay. So we need the 5% damping. You know that, as we mentioned last week, according to the Italian building code, the elastic spectrum related to 5% damping is the only one related to scaling factor eta equal to 1. Okay, so if we just assume the elastic spectrum with a scaling factor, a unit value of scaling factor, then we will scale directly within our design procedure with the proper definition of damping ratio. So, okay, this is very important. We need the elastic spectrum at 5% damping. Okay, then we go to parameters of the response spectra, and they are provided according to period column and elastic spectrum column. And you have just to pay attention to some parameters. Here are all the parameters related to the definition of a seismic hazard for Italian territory. The procedure is the same also for other countries. There are, if there are tools to use, it's better, but otherwise we have just to go through the standard code, the building code for that country, and to see what is the definition of the response spectrum, and then to build it for actually the construction site that we are considering. Just note that units are always a very important issue to deal with in the engineering. So periods are given in seconds, and this is generally provided in all codes. But here the acceleration values are provided in Gs. Okay, so this means that for all our computations, we need to multiply these values by 9.81 meter per second squared, because we need acceleration values for the proper computations measured in meter over second squared. So remember that whenever you see the table of the response spectrum with the G units, you have to multiply those values by the gravity acceleration in order not to have actually mismatching, results with respect to what you are initially guessing. So we have just to easily select these response spectrum, to copy and to paste within our Excel spreadsheet. So let's just remind that this is period in seconds, and these are spectral accelerations in G. Okay, so if we want to be sure, we have just to again define another column, which is spectral acceleration in meters over squared seconds, which is just the previous column value times 9.81. Okay, and we will use these values instead of the first. Okay, so this is okay if you want to consider actually the graph for these. This is actually what we obtain. And you see the plateau, and actually the definition of this response spectrum is also important. You see that this graphical representation of the response spectrum provides the all the points highlighted with markers. Okay, And this helps us to notice that the tool for the Italian building code provided the response spectrum with just 3 initial points, and with the second and the third, you have already defined the whole plateau. And then there is a mesh of points for these 2 branches, the remaining 2 branches, where we have 1/t and 1/t squared as the proportional factors with respect to periods. But just because this additional mesh provides a curvilinear trend for both the branches, but you see that, for instance, for the linear ones, you just provide the external joints. Okay, so this is important whenever you need to provide actually some computations with linear interpolation of results. We have to keep in mind this. Okay. So this was just to see the graphical representation. So now we can start with actually a rubber bearing isolation system. Let's write here the result for the case study structure, which is M total, which is actually the number that we have just computed. We go back to the previous spreadsheet. Okay, and so this is 1,300 tons. So according to these, we have to define actually the minimum isolation period to consider for the definition of our isolation system. So in order to do so, we have also to consider the actually the vibration period for the for the building with the fixed base configuration, and then the behavior factor. And so generally we should need to perform some model analysis for the fixed base configuration to consider the proper behavior factor, and then to consider the actually the spectral coordinates. But now, just for sake of simplicity, we want to consider a very high period value for the definition of the performance point. So let's go through the second step of the procedures that we have seen on last Friday, which is the definition of the performance point. And we define the performance point according to the isolation. We will choose a very high value. Let's start from 3 seconds. And the equivalent viscous damping. So it is just a number. So rubber bearings means that we can choose between low damping rather than high damping. Let's consider 7%. So let's consider it like a low damping. Okay, so these are our main characteristics for the performance point. Okay, now we should go through the third step, which is actually the computation of the global characteristics of the isolation system. So global characteristics. The first one, which can be very easily computed, is the global stiffness, the effective stiffness of the whole isolation system, what we call key easy. Let's call it K isolation. Okay, in kilonewton over meter, which is just a stiffness. And this has to be computed according to the definition of period for a single degree of freedom oscillator. We have the period value, we have the mass. So this is equal to total mass of the building times omega squared, which is 2 times pi, which is 3.14, divided by the period squared. And this is the global stiffness of the isolation system. Okay. Then we need to compute the displacement demanded, so the maximum in meters. And then maybe before the maximum displacement, we can compute directly the maximum force, normalized force with respect to the total mass, so which is actually F max divided by M total, which is actually the spectral coordinate with respect to the acceleration spectrum. These should be meters over square seconds. Okay. So now we have to go within this table, this list of points of the response spectrum to check where we have 3 seconds, and then maybe we need to proceed with some linear interpolation. So you see that here we don't have actually 3.000 seconds, but we have the smallest is I think 3.037, which is this one, but maybe the closest is this one. Okay, so okay, we can do linear interpolation, but we can also choose some approximation because this is just a pre-design. So this is approximately 3. If we remove some digits, you see this is 3. Okay, so let's assume that this is our actually our line for the listed values of spectral accelerations. And so for this value, which is the maximum force divided by the mass of the structural system, which is the spectral coordinate with respect to the acceleration spectrum, we can assume this value, okay, which is related to 3 seconds. Okay. For the maximum displacement, we will use actually the definition of the spectral acceleration and omega squared. So the maximum displacement is actually the spectral acceleration, and this is important. You need the numerical value in the meter per square seconds, otherwise it doesn't work. Obviously, you will get a scaled value. A scaled value of displacements with respect to g, actually, the gravity acceleration. So maximum displacement, which is the spectral displacement, equals to the spectral acceleration times period divided by 2 times 3.14 squared. Okay. Okay, there is maybe, okay, this is, okay, I missed some brackets. Okay, now everything is better. So you see that there is a huge displacement here. So the displacement demand is something like 40 millimeters, sorry, 40 centimeters for 100 millimeters. And actually, this is mainly because we have a very low damping and a huge value of period. And this is also because actually we have not applied the damping. This is also the main reason. We need also to apply the damping factor, which is the reduction factor, which is actually eta. Let's call it here eta, which is just a pure number. This is according to the Italian building code, the square root, which is this expression in Italy. 10 divided by 5 plus 100 times the damping. You see, this is an expression where the damping should be considered as a percentage and not as a number. So we have 91%. Okay, so here we need to multiply times eta. Okay, yeah, it is not that that much lower with respect to the previous computations, but simply because we have 7%, and 7% is quite close to 5%. but surely we will get the correct results for also the other typologies of isolation systems. So once we have the global characteristics, we can go through the characteristics of the local level, so for the single devices. So let's call these new computations as single device characteristics. Okay, so I just take the research article that you have that I've shared within our folder in the Google Drive, and you will see that here there is actually the definition.
Can I ask a question, please?
Yeah.
So it's a bit late question, but the thing is that I noticed that when you calculated the total mass of the structure, that
Yes.
you accounted for 100% of live loads. But I just remember that vibration-wise, we most of the times don't consider that the live load is 100% there. So
yeah, there should be actually, you see, there is a 30% of live loads.
Oh, okay. I thought you accounted for the whole.
No. There is 0.3 times, so that I accounted for 30%. That should be here, but also sorry, here if I did not wrong. Okay, here. Yeah,
okay,
there is.
Perfect.
Yeah, 0.3 means that we account just for 30% of them. Yeah, you're right.
Yeah, perfect. Thank you very much.
You're welcome. Okay, and generally, okay, here there is written 0.3, but in the Italian building code, there is a name actually for that parameter. It is psi2, and I mean, no, psi0, which is actually the a partial safety factor for external loads, and depending on the usage of the building, the typology of the building, there is a different value, numerical value. For residential building, that parameter is actually 30%. So this is the reason why I consider 0.3 times the live loads. And so let's go back to the definition of the low ion damping rubber bearings. The first local, let's say, characteristic for the single isolator is to compute actually the height of the device, and this is according to the definition of the maximum shear strain. So generally, it is commonly assumed and as 100%, as it is written here, but we can have also higher values. 100%, as I told you, represents actually a lower bound for this parameter, simply because for shear strains higher than or equal to 100%, we have a constant value of shear modulus of the rubber compound, and the rubber compound can also be represented by a constant value of equivalent viscous damping ratio. So this is the meaning. This is the reason why we consider at least 100% of lateral shear strain for design. So let's consider this for the computation of the total height. Then there is the definition of the diameter, of the horizontal diameter of the isolator, which is just twice the maximum displacement. And then we have the stiffness of the single device, which is shear modulus times the area of the rubber divided by the height of the isolator, and then just very briefly the number of isolators. So this is very easy. So let's go through these steps. Okay, let's start with the definition of the height. So we have to define the lateral shear strain. So gamma, let's call it D, which stands for design. This is just a number. 1, which stands for 100%. Okay, we can do also like this. Okay, perfect. So we can compute the H isolator, which is the height in meter, which is the maximum displacement, which is the max, so the spectral displacement, divided by the maximum shear strain, which has been assumed. So it is exactly equal to the same amount. Okay. Then we can compute the diameter, the planned diameter of the isolator, which is just twice the displacement. Okay. Since we have assumed 100% of lateral shear strain, we can also assume twice the height of the isolator. But whenever you will assume a different value of gamma, it is better always to refer to the displacement, because this is directly related to buckling and rollout of the device. So let's always consider twice the displacement. Okay, this is important. So you see, we have approximately this size for the diameter, the planned diameter of the device. Now we have to consider for the computation of the stiffness of the single device also the elastomeric compound characteristics in terms of shear modulus. And let's consider GR like in megapascals. Let's consider 1 megapascals, which is a medium compound. Okay. So finally, we have K isolation, small K isolation, which is the stiffness for the single device. We have just to be consistent on units, because here we have G, which is in megapascals, and then we have the diameter and the height, which are in meters. So just pay attention on that. And then I think that I think that the easiest, changing units for us is to change the shear modulus in kilopascals, which means that we have just to multiply 1 by 10 to the third. So we have G, which is 1 times 10 to the third, times the area of the rubber, okay, which is 3.14, which is pi, times the diameter squared over 4, divided by the height. Okay. So in this way, we are computing a stiffness value, which is kilonewton over meters. I just want you to see that, to notice that even though we have computed already the stiffness in kilonewton over meters, we can also compute the stiffness in Newton over millimeters. The numerical value will be exactly the same, because the stiffness in Newton over millimeters is exactly the same number with respect to other units like kilonewtons over meters, because there is the same ratio between Newton and kilonewtons and millimeters and meters. So now we are ready to compute the number of isolation devices, which is just a pure number, and this is equal to actually the K isolation global, capital K, divided by small k. Okay, so let's do something like this. We can round also that number, but just compute the numerical value, and then we will do some reasoning. That's it. Okay, you see that there is a strange number. Okay, 5.2 doesn't mean anything, because we cannot install just 20% of a bearing. We will have for sure to come up with the integers for this parameter. And then, yeah, maybe here we can round it. So we can do some round function for me, because unfortunately I have Excel in Italian, so it is arrotonda. Sorry. Okay. Just with no digits. So we have 5 isolation devices. So this is very uncommon, simply because they are very limited number. This is a limited number of isolation devices, and remember that our structure is something like this. So we have 24 isolation devices. So we need to.
Professor Marco, so
Yes.
the answer that we obtained is 5.2, and then it has been rounded to 5. I thought you're going to round it for 6 instead of 5.
Yeah, actually, we can do both. I tried to 5.2 is much nearer to 5 with respect to 6. But generally, we can do whatever actually, because we have just to try to choose the best solution. And this is not like pre-designing the structural elements. And generally, we used to in structural design, we used to actually to round numbers to the higher integer, or generally to higher values. Okay, because we generally higher values are related to more strength and generally better capacities for the element itself. So here we are providing actually the number of isolators. So maybe if we just install less isolators, we have a minor value of stiffness, so we get a larger period. So we have a larger period shift. So maybe it's better to lower the value of isolators instead of increasing the number of isolators.
So do you consider, for example, that the optimal design is the case where you have number of isolator, the one that you calculate is close to an integer? Like if you get, for example, 4.9, this is optimal design, or 5.9, for instance?
Yeah, actually, we have to go to integers because a number of something is just an integer. Actually, you have to count isolation devices, so it is not something like a parameter or a scale factor, but it will represent actually the number of isolators that you will install. If you get 4.9, I think you can go to it is approximately 5. You don't have to go back to 4. But if you are just slightly higher than 5, like in this case 5.2, yeah, you can go back to 5 easily. Even though also 5 is not the best solution, because 5 is an odd value. So it is not possible for us to install 5 devices in a symmetric way. So we have to change some assumption to come up with the best with a better solution actually.
Okay, so in your opinion, maybe we can change some characteristics or properties so that we can come up with an even number. But
once this is the main reason. I mean the main procedure that I generally assume. I just perform the procedure, the overall procedure, all the computations with Excel, and then I look at the results. If it doesn't work, like in this way, because we have just few isolators, I try to change some parameters in order to come up with the best solution. And this is what we are going to do now, actually.
Thank you.
Yeah, you're welcome. So 5 isolators again. You see, this is the plan view of our structure. So I think that we should provide much more isolators. Okay. And actually an even number of isolators. So we will have to change something for sure. Generally, the reasoning is the following: we get a few isolators whenever we need a very small value of stiffness. Okay. So the first assumption that, the first parameter that we have to change whenever we need much more isolators, we have to increase the number of isolators. Maybe could be the period which defines actually the performance point. Okay. So maybe 3 seconds is too high to provide actually the proper number of isolation system. Sorry. The number of isolators for our system. So let's try to change it. Okay. And instead of 3, let's consider directly 2.5. Okay. And let's consider directly this value, 2.5 93, so that we can come up with the right. We have to change also this cell, which is the spectral coordinates with respect to the acceleration spectrum. Okay, and let's highlight this as the second. I highlighted it in green. Hopefully this will be, so this is the first choice, this is the second. Let's see what happens to the results. Okay, we get 8 isolators. Yeah, this is better. You see that the maximum displacement is slightly lower, simply because maybe we have switched from the last branch of the response spectrum with respect to displacement, which is the constant spectrum displacement, to the previous one, where the spectral displacement varies with respect to a linear function of period. So sizes are slightly different. And with this compound, which is a medium compound, we get 8 isolators. So according to our plan view, maybe 8 isolators could be fair enough. I mean, we can choose these 4 and these 4, okay? And by keeping exactly the same here as flat sliders, rather than 2 here, 2 here, 2 here, and 2 here, and all the remaining points as flat sliders. I think that the best choice will be the LY, the beams along the y direction, the edges along the y direction represented by isolation devices, because in this way we are maximizing the distance between isolators and the stiffness center of the overall isolation system, so that we are automatically increasing the torsional stiffness of the system. Okay, so I think that this is fair enough. So let's consider this solution as our rubber bearing solution. So what we you have seen that we have just changed the isolation period in order to come up with more isolators, and this is because if you get few isolators, this is simply because you need a lower value, a too low value actually of lateral stiffness. So if we want to place more than 4 isolators, 5 isolators, like the first computation that we did, actually you need to increase the number. If you increase the number of isolation devices, you are automatically increasing the equivalent stiffness of the whole system. So if you want to increase the stiffness, you have to lower the value of period. Okay, that is a strategy. Obviously, if you want, also you can also try to consider other compounds. So maybe if you get a soft compound, you see you get 20 isolators. Okay, there are also other values. So a medium compound could be also 0.8, depending on the depending on the producer. What happens is that, okay, 10 is actually an even value. Okay, so it looks like a good definition of the isolation system. But if you go back to your plan view, how do you place 10 isolators in a symmetric way? It is actually impossible, simply because you have an even number of beams along the x, okay, and the same along the y. So the best is to get an even number, and also the halved number should be also even. Okay, so maybe the best solution for this increasing value would be also again to increase a little bit in order to come up with 12 isolation devices. But pay attention that in order to increase from 10 to 12, we have to lower again the isolation period, and then maybe you get too much closer to the minimum isolation period. Okay, so I think that the best solution will be actually what we computed before. So we assume 1 as a shear modulus as medium compound. So we come up with 8 isolators. Okay. So let's start with the, if there is no question, this is, you see, quite straightforward. This is the easiest one together with the curved surface slider. And then there is now the one related to the lead rubber bearings, which is a little bit more complicated, but from the definition point of view. Now that we know that there are some parameters which have actually probability density functions related to some statistical analysis, we can just assume the mode values for all of them, and that's it. So let's just copy this spreadsheet. We call it LRB, because actually we have exactly the same columns which are representative as for the seismic hazard. We have the same equivalent, total mass of the building and the definition of the performance point. Okay, let's start from the same, the same isolation period, 2.5, approximately 2.6. Okay, and then we will change afterwards once we computed the characteristics of the bearings. Okay, what we have to change also here for LRB is the damping ratio. And for lead rubber bearings, we can assume an intermediate value, which is 25%, so 0.25. You see that eta becomes 58% of the elastic spectrum. Okay, this is the effective stiffness of the overall isolation system. This is again the okay, this is the force, but this is for the elastic one. Okay, that should be as well multiplied by eta. We can just move this definition of eta to this. It's better, I think. Note this. I don't know where there is the definition of the damping. We have to modify these. Let's go back to also to this. The height of the isolator. So maybe there is no there is no multiplication by eta. Okay, no, there is eta, so we have just a single cell. Okay, perfect. So instead of having these, we have to change this one. Okay, instead of having the multiplication of eta in the displacement, we have to move it in the force response, so that, okay, also this value is scaled, because otherwise it doesn't make sense to have a not scaled normalized force and scaled displacement. Both of them should be scaled by eta. Okay, so let's change it also here. Okay, perfect. So automatically we have a reduced value of displacement. We can assume again, okay, some of them will change. Let's erase. Okay, let's assume the first characteristic, and we go to the lead rubber bearing paragraph. Again, the first step is the same. We computed the height of the device by assuming the maximum lateral shear strain. And let's assume 100% again. Then there is the second step, which is the computation of the yielding displacement according to the lateral yielding strain, shear strain, assumed as 2.5%. So we have again a gamma design equal to 100%. Let's assume it like this, and then we can change afterwards if we get strange results. And this is the height. Then we can compute, actually, let's compute gamma y, which is assumed as 2%, 0.025. Okay, so dy in terms of meters is equal to gamma y times the height. So you see approximately 5 millimeters of the yielding displacement. And then since we have the maximum displacement and the yielding displacement, we can compute the ductility. The displacement ductility, which is just a pure number, and this is the max divided by dy. So you see we have 40, which is a huge number, but we have always to remind that the yielding displacement is very low. This is the reason why we get such a value. Okay, and according to this ductility and according to the assumed value for damping, we can compute, actually, yeah, this is you see the distribution for the lateral yielding shear strain. And then according to this simplification, as we have seen last week, of the force displacement loop, this normalization with respect to the yielding values for displacement and forces. And we can come up with this definition of the overstrength factor, which is twice the ductility divided by twice plus 2 plus pi times the ductility times the viscous damping ratio. So this is alpha, which is just a pure number. This is twice the ductility divided by 2 plus pi 3.14 times ductility times damping as a number. Okay, you see 2.4. Okay, generally it is bounded between 1.4 and 1.5 and 3. Okay, so according to this, then we can compute the yielding force of the lead core according to this distribution and the mode value for the yielding stress for the lead. And by assuming the diameter of the lead as 80% of the isolation height. Here, I also provided the R² value for the fitting curve associated to the log normal distributions for all the cases, and then also the parameters, so that you can also assume these parameters for parametric studies. So you see, we will assume the mode. We have assumed 2.5 for the yielding shear strain. We will assume 11 megapascals for the shear stress of the lead core, and 0.8 as the ratio between the diameter of the lead core divided by the height of the isolator. So according to these expressions, we can come up with the yielding force of the single isolator. So let's assume all of these. So we have the actually the parameter, which is the ratio between the diameter of the lead core divided by the height of the isolator as a ratio. We assume the mode value, which is 0.8, tau yielding for the lead core as a megapascal value. We assume again 11, which is a mode value. So here we can assume L in meters, which is equal to this ratio times the height, which is previously computed. This is the diameter. Then we have the lead area meter squared, which is 3.14. So pi times the diameter squared over 4. And then we have the Fy in terms of kilonewtons. Okay. So this means that we have actually the multiplication of the shear stress, the yielding shear stress in terms of kilopascals, so by 10 to the third times the area. Okay, so we have 208 kilonewtons, and this is the yielding force of the isolator, of the single isolator. Then we can compute the maximum force as just the kilonewton, as the multiplication between the yielding force times the overstrength, so alpha. Okay, so this is the single force value, approximately 500. And okay, then we can come up with the generally the external diameter by considering the post yielding stiffness, but that is just a geometrical parameter. Let's assume now the number of isolation devices so that we can ensure if the design is correct or not. So we compute the single device stiffness, which is kilonewton over meter, which is just maximum force of the single device divided by the displacement demand. So F max divided by T max. This is the single device stiffness, and then the number of isolation devices is equal again to the ratio between the capital K divided by the single K, the stiffness of the single device. Okay, and then we can round. Okay, then with no digits. Okay, you see 3 isolators. This is quite unusual, and actually it is impossible for us to consider this. So we need to increase actually the overall behavior for our system. So what we can compute is just to again, we can just lower the period, but we are already at 2.6, so maybe this is not useful for us. What we can do is actually to modify the damping. Okay, so if we want to consider more isolation devices, okay, 3 is actually something which cannot be applied. What we should increase is also the force response. So maybe we need a lower value of damping. So let's try to consider 20%. Okay, so we switch to 63%. So maybe we switch from 3 to 4 isolations. Okay, no, it is also reducing because maybe so we have to increase the damping. So let's assume 30%. We go back. Okay, we have 4 devices. So maybe there are also some other aspects to cover. Another issue could be to consider a maximum shear strain, which is a higher value of 100. So for instance, 105. Okay, yeah, still 4. But I think that with 100, okay, that's it. We should consider also these, but because you know, if we increase the period, maybe we get something which cannot be. Actually, let's try. If we consider these like 3 seconds, the previous one, and we change these. you see again, if you just increase the period, you get a lower value of isolation devices. So it's better to go back to 2.6 period, 30% of damping, and we get actually 4 devices. This is okay. This could be better, but okay, maybe this means that the best solution that we can provide with the lead rubber bearings for this particular structure is just to consider 4 isolators, and the best solution would be the 4 isolation at the corners of the plan view of the building, and then just providing a flat slider for all the remaining supporting points. Okay, but generally, yeah, this is not actually the best isolation system that you can design. So maybe lead rubber bearing solution it is not the most suitable for this particular building. Okay, but at least actually it provides with just 4 bearings, it provides a good result. I mean a good performance, simply because we have actually the proper definition of the reduction factor of forces and displacements. Okay, and I think very briefly, this is what we are going to model also on Wednesday. Very briefly, let's try to actually design also the curve surface slider. I just erased this and I just copy this spreadsheet again, and let's assume it has curve surface sliders. This is again always the same, the mass, and then let's erase all these characteristics which will be different for curve surface slider. Okay, so let's consider again 2.6. Now we have seen that for this particular case study structure, 2.6 looks like a good period value. And let's consider for CSS devices also here, just to keep in mind that it is a different typology. Let's consider again 30% of damping, and we get these values again for maximum displacement and the normalized force. Okay, so we know that the definition of mechanical properties is the easiest procedure for curve surface slider, and we go to, okay, these are the main characteristics that we have computed for lead rubber bearings. For curve surface sliders, we have just 2 equations, which is this one for the computation of the design friction coefficient, and for the computation of the equivalent radius of curvature of the whole device. So we have we can just create a new cell for the Xi limit, so the damping ratio for directly associated to the maximum value, which can be computed according to a hysteretic behavior. So Xi limit, which is a number, and this is just 2 over pi, and you see that you get 64%, 63.69, so could be rounded to 64%. And so this is the expression, the ratio between the two damping values times these expressions. So let's go to the definition of the coefficient of friction, which is just a pure number. So this is the ratio between the design value of damping ratio over, so Xi divided by Xi limit, times the normalized force, which is this one, divided by the gravity acceleration, and that's it. You see something like 5% of friction coefficient, and we can compute R equivalent in meters, and R equivalent is G over omega squared, and omega squared is computed according to the assumed value for the isolation period times this ratio of damping ratios, so Xi lim over Xi dim minus Xi d. So let's just write this. We can just add an additional cell for omega isolation, which is in radians over seconds. This is equal to 2 times pi divided by the isolation period assumed for design. This is the omega isolation. So we have G over omega squared times the ratio of damping. And so this is R equivalent. Okay, so this is R equivalent. I just move it here. So R equivalent is 9.81, so G divided by omega squared times Xi limit divided by Xi limit minus the damping ratio assumed for design. Okay, this does not make sense because this is just a pure number. Okay. So you see this is 3.16 meters, and actually this is quite close to the device that we have considered last week for the experimental assessment in the numerical laboratory. 3 meters as equivalent radius of curvature, and yeah, 5%, actually 5% can be returned by a proper application of contact pressure. It has vertical load to the device, but actually 5% is a very common value that which can be achieved for unlubricated materials, sliding materials. So according to these computations that we have performed, we have defined the total mass of the building. Also, we have guessed some initial sizes of all the cross sections for the elements and the geometry. And actually, according to these computations, we have also defined all the isolation systems. And just to remind that for the rubber bearings and lead rubber bearings, we have defined just isolators. So this means that we will need in the numerical assessment. So the on the laboratory on Wednesday, we will have also to model flat sliders in the non-linear hysteretic way. Okay, so we will model all of them, and then we will try to come up with tomorrow. We will come up with the definition of the seismic input. So to carry out non-linear time history analysis according to a selection of 7 earthquakes, natural earthquakes, I mean. And then we will perform the analysis on Wednesday, and then we will compare results of the average results among the selected events to the numerical values of the performance that we have computed here for pre-design. Okay, so generally we will get some higher values also in the single lever response, but maybe the average value, which is actually the one which is ruled by the standard code to be checked, will be close to the maximum displacement which is computed in the design. Okay, so is there any question about this? Okay, so it's done for the definition of the case study structure. Tomorrow we will consider the definition of the seismic input in terms of ground motion time series, and then on Wednesday there will be the numerical laboratory. So thank you all. See you tomorrow and have a nice day.
Thank you very much. See you.
Bye.